Okay, so we've just learned about the idea of what we called an extensional strain rate, and we took as one example thinking about stretching in the one direction and evaluating this component of this velocity gradient tensor. So this is just one component of it, and we also thought about the idea that we could think about the 2-2 direction and the 3-3 direction. I also want to recognize that we can also think about volumetric changes in strain rate. And so we might imagine a piece of material like, say, this eraser, and I might think about compressing it and how fast do I compress it or how fast do I expand it. And we might be interested in an expression that we might therefore call the volumetric strain rate. And to do that, all we have to do is we just have to recognize that what we have is we have a material element of a fixed amount of mass, and when it moves to the new point in space, let's say here, then it's possible that its volume has expanded or it's changed. And so we'll write an expression that connects the mass of the material to its density and its volume, which we can write as this volume element del V. So if this is del x2, and I can't draw it out of the board, I might recognize that del V is equal to nothing but del x1, del x2, del x3. And so we might be interested in thinking about what is the rate of change of that as we move through space. And we can do that by just recognizing that we could write this as a volumetric strain rate would be the initial volume times the derivative of the volume following a material element. So we'll use our material derivative. And to evaluate that, all we have to do is to just substitute in this notation that we have del x1, del x2, and del x3 times d by dt of these quantities, del x1, del x2, del x3. And this is an operator. This is a differential operator. We can use the chain rule to do this. So I can take the chain rule on this element by element. If I do this for the first term, then I'll get a derivative of this multiplied by del x2, del x3. And now we'll cancel with this. So in fact, we end up with this term, firstly. And then I can do the chain rule again. So now I'll take this term and this term, multiply it by the derivative of this term. And again, these terms will cancel. So we'll also end up with a del x2 of d del x2 by dt. And you can see that the third term will be exactly the same, where now I'll take the derivative of this term. These two terms will come out. They'll cancel with this. And we'll be left with d del x3 by dt. And so this looks like exactly what we've seen before. We called this our velocity gradient. So this would be dv1 by dx1, just like we had here, plus dv2 by dx2, plus dv3 by dx3. And we could write that a couple of other ways. We could certainly write that in terms of Einstein's summation convention that way, or if we wanted to be explicit, we could put a sum in here. So unlike before, we're now adding all components up at the same time, and so we can also write that even simpler as the divergence of the velocity field. And so in words, this says that our volumetric rate of change is associated with the divergence of V. A final way, if we were to write this out as a matrix, then we'd recognize that this would have 9 elements in it, and these terms are nothing but the 1-1 component, the 2-2 component, and the 3-3 component. So yet another way of writing this would be to write it as the trace of this tensor called grad V. And these are all ways of expressing exactly the same information, that it's the rate of change of volume following a material element. So that's one way of writing it, but maybe another useful thing to do would be to connect it to this idea of the mass of the system. And so there's a handout that we can step through where you can see this derivation, but very quickly we might express or be interested in expressing the time rate of change of delta m of the system. And mass is conserved, and so as I look at this, if I evaluate the amount of mass that's moving to my new material point, I still have the same mass here, And so the time rate of change of mass in this system should be equal to 0. So I can now use this identity or this definition that I have here. So I could also substitute this in here and say that this is equal to 0, but this must be d by dt of rho del v. So let's use the chain rule on this and expand this. So I might also express this as del v times d rho by dt plus, from the chain rule, rho times d of del v by dt. And these two things added together must be equal to 0 because mass is conserved in our system. So if I rearrange this, then I can easily rearrange this to write this as 1 over the volume times d del v by dt. So that's our rate of change of our material volume is equal to, so if I bring one of these over the other side and divide it through, then we'll see we're going to get a minus sign on this. So we'll have minus 1 over rho, d rho by dt. So those two are equal through using the chain rule, but we can also now connect it to this statement right here that says that this is also equal to the divergence of the velocity field. And this result is something that we'll see frequently as we go forward. This is nothing but a statement of conservation of mass for our system. So it says the fractional change in density of our system following a material element. So if I follow this material element, this is the fractional change in density. It's connected to the divergence of the velocity field. And again, just to remind us, this has units, and it has units of 1 over seconds. So in particular, if something has a positive divergence, if things are expanding, if this is a positive divergence, then because of the minus sign here, it says that the density is going down. Similarly, on the other hand, if I have a negative quantity in terms of the divergence, then this will say that if this is negative, this is the minus signs will cancel, and it'll say that if there's a negative divergence, then the density of a material flow is increasing. So this is a very, very useful statement of conservation of mass. And in particular, we're going to be very interested in this class in flows in which there's very, very little change in density. And so the final statement that we might make that's useful is we might say that for an incompressible flow, what that would really mean is that the fractional change in density is small. So 1 over rho d rho by dt is never truly 0, but it might be very, very small. So we'll say that's 0. That's equivalent to saying that the divergence of the velocity field is 0. And so we'll frequently make this statement that if the divergence of the velocity field is 0, then we have what we'll call an incompressible flow.